All right, so Chapter 8, Section 1, we are dealing with sampling distributions. And so in this section, they're discussing different type of distributions, uniforms, skewed, bimodal, all these different types of distributions. But something interesting happens when we're dealing with the means of these distributions. And I'm going to do a quick example in StatCrunch to show you what I mean. If we look at a binomial, which we've done recently, and we say that it is something that is skewed to the right, right? And we look at its distribution, and we see that it's skewed to the right. As I increase my sample size, I get something that is still skewed to the right, but we can't tell anymore. It looks more normal. We get this normal distribution as our sample size increases. That's something that is similar when we're looking at uniform distributions or bimodal. We see that it has a mean, and then it looks like it's a normal distribution. So when we're dealing with distributions and we're talking about sample means, we get normality. We get that bell-shaped curve, which is awesome because it allows us to figure out a whole bunch of stuff. So on a problem like number 4, we're talking about describing the distribution of the sample mean, x bar. So since I have a sample size of 49, anything larger than 30 is kind of the go-to. I can say that it's approximately normal. I have no idea what it looks like, but I can say with 49, and I'm looking at means, I can say it's approximately normal. And so that's something that I get when n is larger than 30. When I'm trying to find the probability of these things. So first we have to find the mean and standard deviation. Well, it tells me that the population mean is 90, but what's the sample mean? And so in the text, it talks about, get to the text, it talks about the mean of your sample mean is equal to your population mean. But there is a different equation for standard deviation. So we'll kind of talk about that in a second. So the mean is just what my population mean is. The mean of my sample means is 90. My standard deviation, the formula is your population standard deviation, which is 21, and you always divide by the square root of your sample size. So this is a new step that we have to do. So in this case, we get 3. Nice round number of 3, which is awesome. So my standard deviation went from 21 to 3. So now when I'm computing the probability that x bar is greater than 93, we can still go back to our normal calculator, since we can say it's approximately normal. We say that I have a mean of 90. But again, I'm dealing with sample means, so my standard deviation is 3. And I think that one said greater than 93. Right, so that's exactly 1 standard deviation above. So 0.1587. But again, we didn't take just the standard deviation. We took the standard error of the mean. We're dealing with sample means. So we had to divide it by the square root of n. This one, we would just do it and say same values, except I'm looking at less than 84. And the last one, it says a between, and so it's 86.25 to 97.2. So we would just go to our between part of the normal calculator and plug in those values. Now, I want to show something that maybe will help explain. So if we talk about gestation, so women know what gestation is, guys. We should know that's the amount of time from conception to birth. So if we think of human female gestation, we think it's about 9 months, which is actually turns out to be 40 weeks. So let's say there's a 40-week gestation. And for the population, let's say that the standard deviation is 2.5 weeks. A lot of different things come into play here as far as C-sections, what we do in America, but let's just say natural childbirth, we get a standard deviation of 2.5. And so let's get a good picture here. And we can see that 40 weeks, here's the standard deviations, right? Most of us have probably known someone that's given birth a month early. Like, that happens. And so a month would be somewhere around here, like 36 weeks. So if we put 36 in here, 5% of the population is going to give birth about a month early. It happens, 95% to the right give birth after this 36 weeks. So we don't think that's totally crazy. That's not that uncommon. If we're dealing with a population, so let's say I talked to 50 pregnant females and I found out that well, first, let's figure out the population standard deviation, the standard error of the mean for this one. So if it's the population standard deviation is 2.5 and I surveyed 50 women, I get a standard deviation of 0.35. I'm going to go to 4 decimal places, 0.3536. So now the question's a little different. What would be the probability that 50 women, average gestation, was less than 36 weeks? And on this, we see something like this is super small. That's like a scientific notation times 10 to the negative 30th. It is very unlikely that if we took 50 women and found their gestation time, that it would be 36 weeks or below. It would be very uncommon. We would think that they live underneath power lines, or there's something in the water, or maybe we've gone through some evolutionary change where humans don't have a 40-week gestation period. There'd be something strange. So for 36, that would be very uncommon. That's why we changed that standard deviation. It decreases the amount of variation that we have. So that gives a little understanding of what we're discussing in Chapter 8, Section 1. You have to make sure when you're computing these probabilities for the sample mean that you alter the population standard deviation. You have to find the standard error of the mean, so you divide by the square root of it. Also, that rule of 30 is in your text. So greater than or equal to 30, we can say it's approximately normal. So that's where it is in the text.